Good morning, class. This is Mr. DeMarco with another lesson in kinetics. Well, today we're going to talk about reaction mechanisms. And as you see from our first slide, it's kind of like a roller coaster ride. You have to go up, and then whatever goes up must come back down. So when we're talking about reaction mechanisms, we already know reactions involve energy. Well, the mechanism then is the step-by-step process of a reaction occurring in the forward or reverse direction. Now, when this occurs, we need to analyze how this reaction takes place. And in reaction mechanisms, we use and create a potential energy diagram. Now, the reason why it's a potential energy diagram is we already learned in order to have an effective collision, you need enough energy in the right orientation. So sometimes things are going to collide, but nothing happens. Sometimes they're going to collide, but don't have enough energy to finish all the way through, hence potential. And then sometimes they're going to collide and completely go to completion. So we have to take that into consideration when we analyze these diagrams. These diagrams allow us to illustrate how reactions take place in regards to a change in energy. So we're going to analyze diagrams and apply them to our knowledge of energy being endothermic and exothermic. But before we do that, it's a good idea to get used to the lingo or the parts of the potential energy diagram. So in the potential energy diagram, there are a few key components that you have to understand. The first is the potential energy of the reactants. And the good thing about these vocab words, it kind of tells you what the word means by the words that are being used. PE, potential energy, reactants are the ingredients. So this tells me the amount of energy that the reactants contain. Pretty easy. Reactants, potential energy. Second is the activation energy. Now notice, we all know what energy is, and the word activation means to start. Well, putting that in reaction mechanisms and kinetics terms, the activation energy is the amount of energy needed to start a reaction. Now, in these diagrams, instead of writing out activation energy all the time, we use this little symbol called E, act. Act for activation, E for energy. Every reaction needs a little bit of energy in order for it to start. Some involve a lot more energy, and that's how things can be spontaneous or not as well. When we have the activation energy, sometimes they're going to ask you in questions how much activation energy is needed to start the reaction. That always goes from the reactants to the top. Now, the one thing we're also going to have to be aware of is the mechanism can go in both directions. So you're going to see words in questions that'll say activation energy of the forward reaction, or you might see activation energy of the reverse. And when we get into our diagram in a few minutes, I will talk about that one more time. But regular activation energy going forward would be the reactants to the top. Third in our diagram is our activated complex. Complex means something big is happening. Activated tells you that there's action taking place. Well, the activated complex is the maximum amount of energy the reaction can contain. This is the action step. So in our reactions, if it was a synthesis reaction, that would be where the bond is made. If it was a decomposition reaction, that would be the point where the bond breaks. If it was single replacement, that would be the part where there's a single switch. So you get it, that's where all the action takes place. The activated complex being at the maximum amount of energy, well, that's always easy to find because it's the highest point on the graph. Again, as we're doing these potential energy diagrams, if you keep these things in mind, they're pretty easy to understand. The fourth thing in our diagram is the PE of the products. Very similar to reactants, except this time it's for the products. So here I'm going to have the potential energy of the products. So I have my reactant energy in the beginning, and I have the energy that comes out. And what's going to happen is we're going to have a change in energy. And that energy can either be a positive change or a negative change, endothermic or exothermic. The fifth thing in my diagram will be my catalyst. Now, remember that a catalyst speeds up a reaction in both directions, but you have to understand how it does it. And in these diagrams, we're going to see exactly the definition. A catalyst speeds up a reaction in both directions by lowering activation energy, EACT, and providing a new pathway. Again, if you go back to that analogy I used of going from your house to school, there are probably many ways to get there, and some ways are shorter or longer than others. Well, the catalyst provides the shortcut, a new way to get there using the least amount of energy in the fastest way possible. That would be a catalyst. Last but not least is our delta H or our enthalpy. Now, we already know delta H and enthalpy are the same thing, and they mean it's the change in heat. But in these diagrams, we want to be able to visualize and calculate what that delta H value is. So it's the change of heat between the products and the reactants. Change means subtract products from reactants. So when we're doing this calculation, this is where those numbers that we used make sense. If delta H is negative, when we're done, it's going to be exothermic. And if delta H is positive, it's going to be endothermic. So what we're going to do is take these 6 items and put them in a reaction sequence in a potential energy diagram. And again, when you're at home, you could always pause. You can go back to other slides and see the connection that's taking shape. So all we're going to do is take these vocab words and place them on a PE diagram to show how a reaction takes place and show the change in energy. So let's take a look. Here I have a reaction. It's endothermic. We know it's endothermic because the word energy is on the left-hand side. Whenever energy is on the left-hand side, or we see a triangle over the reaction arrow, I know that it's endothermic. It's going to absorb energy in order to occur. Now, I really don't need that word energy there because I also know from my reaction that when it's a decomposition, A, B, C together, and I'm going to break these bonds to get A, B, and C separate, I know breaking a bond is endothermic. So I know that this is endothermic, and we're going to see that at the end that the delta H for this reaction is going to turn out to be positive. All right, now, how do you set up a PE diagram? Notice I have my 2 axes. I have my horizontal X and my vertical Y. On the Y-axis is where we put our potential energy. On the X-axis is where we put our what we call reaction coordinate, which shows us the way in which the reaction is going to proceed. Now, sometimes they will not use the word reaction coordinate. They will just have the arrow. Notice it's a single arrow, but we can use a diagram and talk about the reverse reaction at any given point in time. Now, once we have our axes set up, I need to label my potential energy. Because again, at the end, I'm going to make this statement true based on this reaction. Now, these numbers always vary. In this slide, I went from 0 to 900. Again, could have been more, could have been less, could have been in 50s and 10s and 20s, whatever. I went by hundreds. Now, I am going to put 2 points on this graph. Now, normally, if you were asked to draw one of these, you would be told what the energy is. Otherwise, you can't do the problem. So I'm going to say that my reactants in this diagram have 400 kilojoules of energy. Okay? Now, again, I'm saying that. Now, notice this is an endothermic reaction, which means the reactants have to absorb energy. So that's one of the first things that we're going to be able to notice. If it's an endothermic reaction and my reactants absorb energy, that means my product line is going to be somewhere higher. And again, I chose to put the products at 700. And what I did here was I labeled each one, which normally is not done, but just for our demonstrative purposes to show you what the line actually represents. So the reactants are starting off with 400 kilojoules of energy, and the products are ending up with 700 kilojoules of energy. That's how the reaction is going to proceed. Now, just like that first slide with the roller coasters must climb a hill before the ride starts. That's how every potential energy diagram is going to start. Notice I put my little curl line in. I like to call this line the speed bump because the reaction does not proceed until you get over the speed bump. Same thing. You can't get through the parking lot unless you slow down, unless you want to do damage to your car, and you slow down to go over the speed bump to get to the other side. So this is my general shape for every endothermic reaction. So to get the bond of A, B, C to break, I have to put in all of this energy, and then boop, the bond breaks and the reaction finishes. That would be a characteristic of an endothermic reaction. Now, notice I have not mentioned any of my key vocab words yet, but now we're going to put them in. So if this is my reactants, then this right here would be my potential energy of the reactants. Makes sense. The reactants go on the left, so it's from the bottom to the reactants. Well, if that's the case, then this line, notice I'm going from the reactants to the top. I have to go up this hill to start the reaction. So you're probably thinking, yep, you know what it is, and you probably are right. This is my activation energy. Now, sometimes they might actually ask you what the activation energy is. That's a mathematical question. It's going from 400 to 900, which is 500. That could be a question. Well, on this side, we have our lowest point to our highest point. And remember, the highest point on a graph is the activated complex. Okay, so if they ever asked what's the energy of the activated complex, that would be 900. Okay, sometimes when they want to be a little trickier, they may not have this line in here and still ask you what it is, but from the bottom to the top would be 900. Notice it would be 400 of the reactants plus the 500 of EACT gives you the 900. On this end, the right side of the arrow, notice how I did it. I have my potential energy of my products. Okay, so I'm starting to put my pieces in. So I have 4 of the 6 things that I need. Well, the 2 things that are left, one is this delta H thing. Well, remember, delta H is the change in heat between the products and the reactants. So between the products and reactants, I have this space called delta H. And when I calculate this in a bit, I'm going to find out that it's positive. Okay. But the last thing I'm going to put on this diagram is a catalyst. Now, remember what a catalyst does. A catalyst speeds up the reaction by lowering the activation energy and providing a new pathway. So I put a catalyst in red. And notice what happened. My activation energy did get lower. And I'm not taking the big hill. I'm taking the pathway with a smaller hill. That's the providing a new pathway. So that is my catalyst. Sometimes they might ask you in a question to draw the catalyst when the activation's lowered to a certain amount. In this case, my activation energy probably went to about 750. Okay, So my new activation energy wouldn't be 500, it would be 250. Again, just a question that could be asked based on our diagram. So the last thing to do on this diagram is to find out what this delta H thing is. Well, if I know it's the products from the reactants, I just have to analyze my numbers. It's going to be 700 minus 400, which gives me a positive 300. This just reinforces that this reaction is endothermic. So these are all the parts that show up on a graph. Once in a while, you'll see that they move the lines around and ask you for the same pieces. Okay? I put them exactly where they should show up. However, if I take this delta H line and let's say I slide it all the way over here, it's still between the reactants and the products. It's still delta H. It doesn't matter where it is. If I took this activated complex line and slid it over to here, it still goes from the bottom all the way to the top. So that's questions you could be asked about, where lines are not in the exact spot they should be, but they represent the same values. Last but not least, as I mentioned, sometimes they're going to ask you about the reverse reaction. Well, right now the reaction is going this way. So that's the reactants and that's the products. Sometimes they might ask you for the activation energy for the reverse reaction. Well, now I'm going this way. So my activation energy would be from here to here. In this case, it would be 200. So again, not a hard concept, but if you're not careful, you can make silly mistakes. So that's our example of an endothermic reaction. So now I'm going to walk through an exothermic reaction, and then as always, you'll have your worksheet to do at the end. All right? Now, if you know what an endothermic reaction looks like, an exothermic reaction is going to be similar with one key difference. So let's take a look at it. Here I have an exothermic reaction. And notice why I know it's exothermic. I now have energy on the right? I also know from my reactions, well, now I'm taking these three things that are separate and I'm making a bond. Always exothermic, which means in this case, the connection delta H has to be negative. Remember, exothermic means release heat. So if I say that my reactants have 600 kilojoules of energy, well, exothermic means I'm releasing energy. So my products, are going to have to be lower. Now, again, I am arbitrarily putting these points on the graph for myself for this slide, but you'll be told if they want you to draw one, what the numbers are going to be. So as I did on the last slide, I'm labeling my reactants, I'm labeling my products, and that's the only difference. In an exothermic reaction, my products have to be lower. The shape of the diagram does not change. It's like a roller coaster. You must go up before you go down. Notice here the height of which it goes up is a little different. That does change from graph to graph based upon what you're using, but it's still the same shape. I have two flat lines left and right, and a roller coaster up and down in the middle. So now I have my general shape of an exothermic reaction where energy is released. And I see that because it goes from 600 to 200. Well, now I want to put my lines in. So PE of reactants, This time, PE of products. You don't have to go in order as we did last time. I could switch around. I have my EACT, which in this case goes from 6 to about 8, which is 200. I have my activated complex. I need my delta H. Notice how I moved it out of the middle so it's not as crowded, but it's still between the products and the reactants. And then I need to put my catalyst in. In red, notice the catalyst lowers the speed bump, the activation energy, and provides a new pathway. The catalyst starts and stops always at the same points. That does not change. It's just the middle that changes. And that will then give me my catalyst. So once again, the last thing to do in this diagram is to make the connection of exothermic and delta H. Knowing that delta H is products minus reactants, it would be now 200 minus 600. And that gives me a negative 400. All right, so that's the connection. It's going to lose 400 kilojoules of energy because I'm making the bond to become more stable, as we saw in bonding. So again, nothing too crazy here. At first, there's a lot of vocabulary, but once you get the hang of the diagrams, these questions are the easiest ones to answer. You just got to be a little bit careful. All right, so you know the routine. It's going to be your turn to take a look at the worksheet and answer it and turn it back in. Have a great day, everybody.